In today's video, we're going to explore the three main states of matter, which are solid, liquid, and gas, and understand how substances are able to change from one state to another depending on the energy they gain or lose. To help explain this, we will be using a simplified model known as particle theory, which allows us to visualize how the particles within each state behave. In this model, each particle is imagined as a tiny solid, inelastic sphere that cannot be compressed or reshaped. Starting with solids, the particles are held together by very strong forces of attraction that keep them closely packed in fixed positions. These particles form a neat, regular lattice structure. Because the particles are not able to move from their positions and only vibrate slightly, solids maintain a definite shape and volume and do not flow like liquids. However, the particles are constantly vibrating in place, jostling against one another as they absorb energy from their surroundings. When a solid is heated, the particles begin to gain more energy, and this causes them to vibrate more rapidly. Eventually, if enough heat is applied, the particles will have sufficient energy to break free from their fixed positions. This happens at a specific temperature known as the melting point, where the solid transforms into a liquid as the structure breaks down. In a liquid, the forces of attraction between particles are weaker than in solids, allowing the particles to move around more freely, while still remaining relatively close together. The arrangement of particles in a liquid is random and less ordered than in a solid. Despite this freedom of movement, the particles are still compact, which is why liquids have a definite volume. However, since the particles are not held in a fixed pattern, a liquid can change shape and flow to fit the shape of any container it is placed in. When a liquid is heated further, its particles gain even more energy, move faster, and eventually reach a temperature known as the boiling point. At this stage, the energy is high enough to completely overcome the remaining forces of attraction, and the particles escape into the air, turning the liquid into a gas. In gases, the particles are far apart and experience only extremely weak or negligible forces of attraction, meaning they are free to move in all directions. This freedom of movement causes gases to spread out and fill any available space, which is why gases do not have a fixed shape or volume. They are described as moving with random motion, which can be a little misleading. Gas particles actually move in straight lines, but change direction when they collide with each other or with the walls of the container, leading to a constantly shifting and chaotic pattern of movement. If we heat a gas, its particles gain even more energy, which causes them to move faster and spread out even more. In an expandable container like a balloon, the gas will expand as the particles push outward. However, if the gas is held in a rigid container, the faster-moving particles will cause an increase in pressure instead of expansion. Conversely, when a gas is cooled, the particles lose energy and move more slowly. If cooled sufficiently, the particles no longer have enough energy to overcome the weak forces between them, and they begin to form bonds, transitioning into a liquid in a process called condensation. Continuing to cool the liquid will reduce the energy of the particles even further. When they no longer have enough energy to break free from the forces of attraction, the particles become locked into fixed positions and the liquid freezes, turning back into a solid. This entire cycle demonstrates how energy input and removal affect the state of a substance. It is important to note, however, that the particle model we are using is not a completely accurate representation of real matter. In reality, particles are not perfectly solid, inelastic spheres. Instead, they are atoms, ions, or molecules that vary in shape, structure, and behavior. Furthermore, this simplified model does not provide specific information about the forces of attraction between particles, such as how strong these forces are or how many exist between individual particles. Despite these limitations, the particle model remains a helpful way to simplify and understand the otherwise complex behavior of matter during changes of state. It gives us a foundation for visualizing the structure and energy changes that occur in solids, liquids, and gases. That wraps up today's explanation. So if you found it helpful, feel free to share it with your friends and classmates, and we will see you again in the next video.